For this course, I will be using the Redis Insight platform, which is free, so I recommend you use this tool too. First, you will need to create a free account with the Redis Cloud in order to download Redis Insight. Here's a website that shows you how to create an account in a step-by-step fashion. First, create your free account using this link. Once your account is made, you want to make your RedisGraph database. That is outlined on step 6 and step 7. Once you've created the database as per instructions here, now you're ready to download Redis Insight. Go to the bottom of this page and click Connecting to the database using Redis Insight. This should bring you here. Then click New to Redis Insight. That should bring you now here to Getting Started with Redis Insight. When you scroll down, you'll see that you have options to choose your operating system in order to download Redis Insight. So choose your operating system and download it. That should allow you to connect your newly made dataset to the Redis Insight platform. To do that, follow the instruction here that's further down in the page New to Redis Insight tab. Here, you want to click I already have a database. Then you want to click Connect to Redis database. Then you can add your Redis database by adding your host and port, which should be under the details in your earlier database. Just a note here, I have downloaded the Redis Insight version 1. I recommend you do that too. In most lessons, we will be building our knowledge graph using Cypher. You can find a list of queries to create all of the example knowledge graphs in the chapter's slides notes. Furthermore, Redis offers a GitHub repository of different datasets, one of which I will be using in later chapters. I'll show you how to do that. So navigate on your left in the Redis developer page for Query, Visualize, and Manipulate Graphs. This will outline you how to do the visualization, but more specifically, I want you to clone the Redis Git repository for their Game of Thrones demo graph. You can do that by following their steps 14 through 16, which is found here. Now you're all ready to get started on your RedisGraph journey. When's the last time you mapped out your knowledge? Maybe you created a to-do list for your groceries, or did a brainstorm of ideas for your next groundbreaking startup. These are both great ways to organize data. But when these pieces of information start to have complex relationships, like mapping out Amazon products with item numbers, prices, reviews, customer deliveries, and supplier details, we need a scalable way to map data. This is where the knowledge graph, a graph base that encapsulates concepts, entities, and relationships, comes into play. This video will create the foundation of understanding key concepts of the graph that will make the rest of the course easier to digest. First, let's cover some terminology. In building a knowledge graph, there are some components that help represent the facts that we would like to embed in the graph. We have components called vertices, which are sometimes referred to as nodes, and edges. Let's say that we want to embed the following fact into the knowledge graph. Tech.io is a company that has an office in the UK. We can translate the nouns to vertices, so Tech.io and UK are two distinct vertices, and the relationship between the nouns has an edge. So here, the edge has type has an office in. Furthermore, each vertex has a label that describes what type of vertex is added. For example, the UK vertex has a label called country, and the Tech.io vertex has a label called company. This example is very simple, but you can imagine that as you add more and more of the nodes and edges, simple building blocks can quickly scale into a web of valuable knowledge. Big enterprises that harness the power of knowledge graphs include Google, Amazon, and NASA. The flexibility of the architecture allows for encoding knowledge for a range of topics, from medical ontologies to employee statistics and even to the movie industry. Knowledge graphs are incredible at encapsulating data and reveal insights that can only be seen once mapped out. It is a powerful tool, and thanks to RedisGraph, a lightweight graph database module from Redis, as seen here, we can get started right away with building our own knowledge graph. Now that you've learned what the knowledge graph is and its terminology, that nodes are representative of entities and edges are the relationship between those entities, we can get hands-on. So, you're ready to get rolling with creating a knowledge graph, and you've identified the RedisGraph as your graph database module. Now, let's quickly learn how to read a Cypher query, the query language needed to interface with RedisGraph. The complete documentation of all the commands is right here on Redis's Quick Start Guide. If we go to Commands here and select Query, you can see there's a lot of flexibility around querying a knowledge graph and around embedding information into the graph. There's a lot to cover here. I can keep scrolling. But here, I'll show you the basic structure of these queries so you can better understand the Cypher commands and familiarize yourself with executing queries. This is a Cypher query. Reading from left to right, this command type shows us that we are querying a particular graph because it says in all caps, graph.query. There are other commands like graph.profile, which is very similar to graph.query, but will not return particular elements, but instead executes an action plan that is specified in the command. Graph.delete is a command that completely erases a graph and all of its contents. If you want to run a particular query but wanted to inspect how this will be carried out, the command graph.explain will let you do exactly this without actually running the query. Graph.slowlog is also a command to help you inspect the graph and will identify up to 10 of the slowest performing queries and return those queries to you as a list. Updating or changing the graph configurations will employ the command graph.config. Finally, we have the command graph.list, which lists out all of the unique properties contained in the graph. Now, back to graph.query. Once we see this command, graph.query, the next argument is the name of the graph. Here we have the graph called employees. Remember, this graph name needs to be unique in your workspace. The following argument after the graph name is the actual query. Our query starts with match. This means that the graph will be searched for a particular relationship pattern. The pattern we're looking for is a source node connected to another node with a particular edge. Since nodes are always in parentheses and edges are in hard brackets, without even looking at the details, we can see what relationship pattern we are looking for. Another concept that is useful in Cypher is the use of an alias. This is like a variable that can take the place of an element, so we can refer to it later in the query. In this query, P is our alias for the source node. Manager is a label under which this node is marked. Office is the relationship type, and the type of the destination node is location. Inside these curly brackets are the filters for the destination node. In this case, we require the name of the destination node to exactly match Oxford. Finally, the return command will allow you to define which properties you'd like to see returned after executing this query. In this case, we want to see the alias P, so just the source code. Congrats! You have now read your very first Cypher query for a knowledge graph. How would you like to map out your ideas and data in a knowledge graph? Especially in a business setting, time is valuable, so being able to quickly and painlessly demonstrate the value of your knowledge graph is essential. We've chosen RedisGraph as our graph module because it is a cheap and quick way to implement our prototype knowledge graph. For example, in the past, I've used RedisGraph to map out medical ontologies. Once I got used to Cypher, it took me a few days to create, present, and deliver a prototype to my colleagues. The graph contained about 1,000 clinically relevant diseases, which is a tiny subset in the grand scale of medical knowledge, but it was enough to convince the rest of the team that a RedisGraph-powered medical ontology was the best tool to implement to production. RedisGraph offers a quick start for knowledge graphs and an easy-to-learn starting point as an introduction. Make sure that you already have installed Redis Insight, which I've covered in the What You Should Know video. I've already spun up mine and am interfacing the knowledge graph with Redis Insight. This is all free and comes with easy-to-use examples. The other graph module I've used before is AWS Neptune. But personally, I like RedisGraph because it is very cost-effective for the particular database of size around 200 megabytes, which I was using at the time when I was implementing my prototype. With the benefits of large enough memory, AWS compatibility, data persistence, and multi-region capabilities, Redis offers all the necessary characteristics that its competitor, Neptune, is offering too, but with the added benefit of costing only $41 per month, rather than the $200 per month billed by Neptune. That had a big impact on our finances, especially because we are a startup. Don't worry, in these lessons, we are using only the free membership of Redis. As you decide to scale your data, you can choose different memberships to tailor to your needs. You'll discover in this course that even in the free tier, RedisGraph offers a precise, speedy, and large database allowing for a global overview of the whole knowledge graph landscape. Think about a piece of knowledge you'd like to embed in your knowledge graph. Nodes and edges are key components in a Redis graph that represent your knowledge. I'll demonstrate in this video how to add these elements using Cypher. For example, I want a recommendation tool for my brand new online website. I'm mapping out all of the possible data about an ergonomic office item, and I want to embed the fact that my keyboard is an ergonomic split keyboard that comes in colors silver and black. You see that we have the concept like keyboard, ergonomic, split design, silver, and black. And each of these words have a special relationship with our central idea, keyboard. These keywords become nodes in our Redis graph, and the relationship becomes the edges connecting our various nodes. Take a moment to reflect what type of data you're embedding in the knowledge graph. Will the nodes be objects or more abstract? What sort of insight do you want? Would it be more advantageous for you to group different types of nodes under certain topics? Are your nodes independent concepts, or do you need to break them down to smaller parts to accurately embed your data? From this early stage, I want you to sit down and critically think about how you define your nodes and edges, which in turn will influence how you will extract information from your Redis graph, and the kinds of insight you hope to see once the mapping is completed. When you're putting together a data analytics report, you don't open an Excel sheet and randomly pick the x-axis and the y-axis for your graph, right? You decide which dataset is most relevant, put in the independent variable on the x-axis and the dependent variable on the y-axis for your graph, so you can represent interesting findings. This is very similar with the knowledge graph, which is also a graph and requires this kind of preparation. Nodes and edges are deceivingly simple concepts, but because they are the building blocks of a knowledge graph, they will define the mapping of your Redis graph. Let's say we want to embed a fact into the database. Andrea Ghez won a Nobel Prize in the category of physics. A quick note here that nodes and vertices are synonymous, and I'll be using these two words interchangeably from now on. Here, vertices denote the nouns, Andrea Ghez is a noun and our first node, and physics is also a noun and is our other node, as you see here. And edges represent relationship between these nouns. To recreate the visualization you saw in the last slide, we use a create operation. This is the Cypher language. It creates a person node, an edge with the hard brackets, and another category node. Let's try this in our Insight platform. First, you need to create a graph. Click the Add Graph button, and let's put in a Nobel Prize graph called Nobel. That should give you a tab with all of your graphs in a list. Select your Nobel Prize graph. I've copied over the query I've just shown to you in the presentation and taken what's just inside the quotations. A note here that RedisGraph Insight automatically selects the graph with the tab up here, and I'll assume that you're running a graph query, so making your query succinct and easy to visualize. Let's run this. Now we've created a few labels, nodes, and relationships. And now we can visualize that we have indeed created a two-node with an edge between. Now that we've covered how to spin up a Redis graph, the terminology of knowledge graphs, and how to use the create operation in Cypher, you now know that Cypher can add nodes and edges. It is very straightforward, as you saw in this demo. But remember to be thoughtful about defining these building blocks so that when it comes to extracting insights from your final knowledge graph, you're setting yourself up for success. Let's say you've set up some nodes and edges embedded in your knowledge graph, but now you've gained more information about a particular node. How can we connect those pre-existing nodes with new edges and nodes? You can query for entities and create new elements surrounding those entities using the match operation. For example, the original embedded data says, Andrea Ghez won a Nobel Prize in the category of physics. To flesh out the visualization and to encode the full sentence, in 2020, Andrea Ghez won a Nobel Prize in the category of physics and is from the US. We need to connect the Andrea Ghez node with the year 2020 and the country US. So how to do this? Open your Redis Insight. I've already created a graph called Nobel with our Andrea Ghez information about her physics Nobel Prize. An easy way to quickly visualize your graph in Redis Insight is by querying for all nodes. You do that by saying match bracket A return A. Now how do we add the year 2020 and the country US to the Andrea Ghez node? We do this like this. We start with a match where we're looking for a person. A is our variable here that we'll reuse later. A.name equals Andrea Ghez. This is who we're looking for. And we do a create operation where we're looking for the pattern person node is from this country. We also want to add a year node. You can do that by adding a comma with a specific value 2020. We want to connect that with a receive the award and connect that to our final person node. Match a person where the name is Andrea Ghez and create a node is from country. Another node connected with receive the award, another node. Great, that's successfully created. One of the neat things about this UI is that you can double click an old historical query and it'll copy paste it for you in your UI. Great. This worked. Now let's expand to more Nobel laureates. For example, I want to encode the fact that Emmanuel Charpentier won a prize in chemistry and Louise Gluck won a prize in literature. We can do this with our historical queries. So let's go to where we created our Andrea Ghez node. Double-click that. And we can change the name to Emmanuel Charpentier instead of physics, chemistry. You can do multiple of the same query by doing Shift-Enter to create a new line. And here we want to change to Louise Gluck. And she won it in literature. Great, 4 nodes created and 2 edges. Perfect. Let's visualize that again. We see what we expect. With the Andrea Ghez node and the new Emmanuel Charpentier and Louise Gluck nodes. Now that we know how to create nodes and match for specific nodes, you can see with this demo that you can already get a glimpse of how adding more nodes and edges can add depth to the knowledge graph represented in the database. As the data grows, being able to query the knowledge graph for insight becomes increasingly important and translates to impactful business knowledge. By now you've noticed that the Redis Insight platform offers UI-friendly visualizations that allow you to inspect your graph in an intuitive way, where nodes are depicted as circles and edges as arrows. However, sometimes you may need to interact with your knowledge graph without the visual aid, such as an implementation through terminal. I can attest that this is not the prettiest and visually captivating interface into the graph. So, how can you check that the graph is what you wanted to create and what you intended it to look like? In this video, we will cover quick sanity checks using Cypher, such as how to find the number of nodes or list edges. Let's quickly have a look at what I've already created. I've created a Andrea Ghez node that's connected with physics, also connected with the year 2020, which is the year she received the award. We also have where she's from. I've created a few more nodes here too. Emmanuel Charpentier, Louise Gluck. This is all great looking at the UI. Another great way to have a look into what your graph actually has is to do a count. So you can match for all of your nodes and return not your nodes, but the count of your nodes. This will give you a number. We have a count of 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. This is what we expect, and that lines up with our count. You can also have a look at the UI. Here, I'm matching for a node and returning those nodes. It gives you a visualization. But if you click this tab, Table View, instead of giving you a visualization, it will show you a list of all of the different nodes. This has the property name Andrea Ghez, Physics, US, and so on. Let's check for a pattern rather than the nodes. You can do this by saying match. We're looking for a node that's connected to an edge that ends up with another node. And return the count of how many edges we have. We have 5. Let's check if that's what we wanted. That's 1, 2, 3, 4, 5. Great. All of this lines up with our visualization. Now let's execute another addition. Let's say I want to match for a person, Emmanuel Charpentier, and create a is from country France and another node edge node pattern with the year 2020 received the award in. Have a think. How many more nodes do you expect? Do you expect 4 more nodes? 3 more nodes? 2 more nodes? Let's have a look. Let's run that. So earlier we saw that our count returned 8. By adding the country node and the year 2020, think about how many nodes you're adding. And we can double check how many we have by double clicking here and doing another count. The count is 10. Is that what you expected? Let's take a look at what we have in our graph. It might have not been exactly what you expected. You have to take into account that when you create a new node, even if it's exactly the same year, 2020, if you don't specify, it will create a duplicate. So in Emmanuel Charpentier, we have is from France and received the award in 2020. That's a different 2020 from this 2020 that we embedded with Andrea-Guess. These are some quick checks that you can implement as you develop your graph. Being able to identify and verify components of the graph will help you identify issues early on. Imagine you've obtained a new dataset you want to add to your knowledge graph, which makes an old piece of information no longer true. What would you do? You replace the old with the new, but breaking this down further, you need to delete the outdated data points and add in the new. This is where the delete operation comes in handy. In the context of RedisGraph, this is an important operation to make sure to use when you realize that you have made a mistake in the graph or need to update old information. The more you learn about the fundamental operations, the more you'll appreciate how flexible this RedisGraph is to cater to your own dataset, especially on deleting and disconnecting nodes. I'll show you how to do this in this video. Take a look at this script. Do you see a problem in this operation? This is actually not a deadly error. It will run, but notice that we have repeated the chemistry node twice, once for each person. This means that we have a redundant node. To fix this, there are several methods. The easiest is to delete one of the chemistry nodes, which will automatically delete the edge between them. Then, create a query that searches for the chemistry node that we did not delete, and attach that hanging person node to the remaining chemistry node. To specify which of the duplicated nodes to delete, we use the unique ID on each of the nodes, where it is assigned at creation. Here's my Redis insight. Have a look, and we see that there are 2 chemistry nodes. When you hover over it, you can see the IDs, ID 1 and ID 3. The script match for the category with the name chemistry, return ID. This looks for all of the ID for the chemistry nodes. As we expect, there's ID 1 and 3. Let's choose to delete ID 3. So we are matching for the category C, where specifically we're looking for the ID of C to equal 3. Then instead of returning, we want to delete C. That was successful because one node was deleted. Let's have a look at what's going on in the graph now. So we have one node that's hanging for Louise Gluck. Now we have to match the Louise Gluck node to the chemistry node. So how do we do this? We do this by matching the person. So which person are we looking for? We're looking for the name equal to Louise Gluck. Close that curly bracket. And we're looking for the category where this name is equal to chemistry. And what we want to do is to create this pattern. Won a Nobel Prize in. This is the create operation that we're doing. Node, won a Nobel Prize in, node. So we're creating this edge. Let's hope that runs. Looks like it's thinking. Okay, let's have a look at what we've done. We're matching a person where the name is Louise Gluck. I already see my problem here. We don't need that. Okay, we can do this another way. We can match for this person, and instead of using the where operation, you can also use curly brackets. So here we're matching for a person with the curly bracket, name equal to Louise Gluck. Let's close that curly bracket. And we're looking for the category where, let's call for its ID. So I think we had the ID, so we deleted 3, which means we have 1 left over, where our ID for C is equal to 1, and this is what we're creating. Looks like this would be all right. Okay, let's give this a shot. Okay, so this relationship was created. Let's check what's going on in the graph now. As we expected, there are no duplicates, and both persons are connected to the chemistry node with won a prize in edge. Great. You may also repeat this operation by deleting a specific edge with a unique ID, because edges have IDs too, and reconnect the hanging nodes. This means that you have to go back in, take the extra step to delete the disconnected node, so the method that I just showed you is more efficient to deduplicate our work. As you can see, the delete operation is very useful and has neat properties like disconnecting nodes when an edge is deleted, or automatically deleting an edge when a connected node is deleted. With this delete operation in your toolkit, you are another step closer to personalizing your Redis graph. Nodes and edges are both terms that you're very familiar with by now. But what is a type or label in the Redis graph? Can you have a node with a type, or can you have an edge with a type? Can you have more than one label per node? Let's recap these elements so that we can start utilizing the full data at our disposal within RedisGraph, including creating and amending data properties using the set operation. I've created the person node, and I've been using Louise as an example from the previous Nobel Prize winners. But let's say she has multiple interests and is, for example, an avid photographer with a passion for Nikon cameras. Let's embed that. We match for a person node with the name Louise Gluck. We then want to create a node connected with owns with our camera with the name Nikon. Oh, it looks like we have an error. Let's troubleshoot that. Person name Louise Gluck. Close the brackets. There should be a hyphen. Owns camera name Nikon. Okay, that was successful. Let's match for everything. Okay, I see a Louise Gluck down here. Good. So we have a Louise Gluck who has won a Nobel Prize in Literature and owns a Nikon. We've set our Louise node with a person label, as you see here. This is a person label, and has a property name Louise. This label tells us what the node is describing. We can have multiple labels on a node that describes their general type. For example, Louise can be both a person and a photographer if we wanted. And remember, edges have exactly one type that describes what they represent. The type tells us the nature of the relationship. Next, all important information on a node are called properties. For example, a name is an important property. Sometimes called an attribute, we can add more properties per node. To add a property of the camera lens size, we type this. Match for camera with the name Nikon. Let's set n.lens, which is our new property, to be 70 millimeters. And let's also add another property, which you can do by just adding a comma. File type equals raw. Good, 2 properties were set. Let's have a look at that. Let's return match camera. We have one camera node here, and it might be easier to just actually list the table view. We have the properties name, Nikon, lens, 70 millimeters, and file type raw. Great. To amend a property, we can overwrite the information using an equal sign. What I mean by that, let's copy that over. So we're looking for a camera and set the lens to, let's delete the file type. Instead of 70, I want it to be 80. Let's run that. Okay. Let's copy that over. Take a look at our camera node, still there. So instead of 70 millimeters, we now have 80 millimeters, and it's been amended. Or to delete, use a set operation with a null input. I'll show you how to do that. Let's say we want to delete our file type. But we don't necessarily want to delete the whole camera. We set this to null. Now let's have a look at that again. Good, we haven't deleted our camera, but we have deleted our file type. So we've updated the lens size from 70 to 80 millimeters and added and deleted a new file type in the node property. The set operation allows us to amend the Redis graph at ease. By learning how to update information in the graph, you can handle dynamic data and relationships and maximize the potential of your knowledge graph. Imagine your Redis graph is populated with thousands of nodes and edges. Your data is rich, thorough, and ready to give you a treasure trove of insights. This is all thanks to your hard work so far, and now you're ready to create this vast network of information. You will need the correct tools and commands to manage this huge amount of data. There's lots of extraneous information hidden in there too. So, how can you pinpoint the exact balance of querying without missing out on data while weeding out unnecessary information? You want to be smart about which bits of the graph you want to return to you for further inspection. The return command in Cypher is a great way to tailor what results you see without compromising the query itself. By that I mean, the query will scan through the whole graph, but by showing specific information associated with a node, you can filter the result. This is my Redis insight. I've made a social graph made up of peoples and their accounts and who they're connected to. You'll find the queries to create this graph in your slide notes. If I blindly ask for information on these nodes, I'll get all the details, from the unique ID numbers to all the properties on the node. So this is a set of data on a social media account. Who's friends with who and who posted when. And if I filter for all the people who joined the platform in 2022, I would get all the information on the individuals. This is too much. This is how I would query for all the people who own accounts. We go match person connected to owns, connect that to all accounts. And we want to return P and A, which are the person and accounts. The visualization looks straightforward, but let's actually look at what we get in our table view. There's a lot of information in there. Say I wanted to create a mailing list for all new accounts added in 2022. To streamline this, our query remains the same, but I only want to return the associated emails. I don't care about their account names, I don't care about their account IDs, or even the individual's name. We do that by copy-pasting what we just saw and being more specific on the return. So all I want is that account's associated email. We do that by saying I want the A account node, but only return the email property. This will give you a streamlined list of all of the emails associated to all of these accounts. We see 1, 2, 3, 4, 5 here, with a duplicate on alex@gmail.com. More nifty commands that I use often with my return operation is the distinct operation and the count operation. The distinct operation takes the result set and removes any duplicate from this result. It doesn't change the actual graph. For example, here we have a duplicate of Alex's email. So instead of just doing a return, we add the command distinct. You see that we've gotten rid of the duplication. The count operation is useful if I just need a total count of number of the result set. So for example, I can take the query to find all the new accounts made in 2022 and run the results count command. And put all of the account numbers in there. You'll only see the total number of nodes. Here, it matches to 5. The count operation is a part of a list of aggregation functions because it's a type of operation that looks like an aggregated result set and gives back the required answer. This Redis commands website will show you all the different kinds of queries you can make, including the aggregations that I just mentioned. You can find them here. This is similar to the group by command in SQL. There's a full list here of aggregation functions in the RedisGraph commands page. We have functions from max, min, standard deviation, and sum. As the dataset becomes larger, sometimes we want to see certain attributes of the node, but nothing else. Being able to filter information from the resulting nodes can help inspect the graph more efficiently. Do you filter your results on datasets when they return too much information? I have situations when using the RedisGraph where I'm only looking to inspect the results. I'm running a few test queries and want to see just a few example results to make sure that the data is what I expect to see. Sometimes you just need a small sampling of the result to inspect your graph, or maybe you need to specify a certain order of the returned objects. In these cases, the limit and order by operations are very useful clauses when specifying how results should be returned and allow you to tailor the resulting dataset. As an example, I've already uploaded a Game of Thrones dataset, which is available to clone from RedisGraph's GitHub repository. I've outlined how to download this dataset in the What You Should Know video. Let's see how many nodes there are in this graph. We have more than 2,000 character nodes in here, which is manageable, but we don't really need to see every single node and their corresponding information. I want to see a small subset to see what the data looks like. Are these names of characters that I might know? Are they characters in English? Or are they from other parts of the world? Or from a fantasy world? What exactly are the house nodes? Let's first limit the amount of returned characters to a certain amount of names. This is queried by matching for the character nodes and returning these nodes results, and then limiting the number so you only see the first 5 names. Here we have 5 distinct names, seemingly random in the selection, but if you look at the ID, we can see that they all have the same ID until the last letter. A, B, C, D, E there. So they have been ordered by ID. But if I want to order the return lists in a particular way, I do that by adding the order by operation. Let's order the returned list by name. So we match the character nodes by returning the nodes and then order by our character names and limit this to 5. We get all the top A names. Great! You see here that if no sort order is specified, it defaults to ascending. We can also reverse the order by applying the DESC command, which is shorthand for descending order. All we do is copy over our previous query and add the DESC command after our property that needs to be sorted. So .name DESC, limit 5. Now we have the Z names, but also this NaN name. In computing, NaN stands for not a number, and you can interpret this as an undefined variable. For NaN, it looks like we have a female character without a name. This might be a mistake, or it is a certain anonymous character. However, I want to exclude this. If I decrease the number of the last value to limit to 1, I get this undefined character, which means that in the descending list, the NaN character comes up first. So I need to exclude the first value in the descending orders list, which can be achieved by repeating the same query, but adding a skip command. The skip command will skip the first however many objects you define. So here, just skip 1. So DEC skip 1, and let's pull up the limit to 5. As you see, it has excluded the NaN character and gives you all the Z names in the ordered list. Order, skip, and limit commands add more structure to your return operation, allowing you to manipulate the data you see and tailor to your project needs. With so many nodes, wouldn't it be useful to specify conditions on the query? Having more tools to transform your query to give specifying commands will enhance your ability to inspect your graph. Look at this GOT graph. There are so many nodes. Thankfully, there is an inbuilt dashboard on the upper left corner here that gives you an overview of the graph content. The UI for Redis Insight can tell us the label names we're looking at. Here, we have 3 writer nodes, 12 book nodes, 438 house nodes, over 2,000 character nodes, and over 500 edges that's called belongs. With so much information in one place, restricting the results we see will speed up inspection and help you understand the content of your return query without overwhelming you with information. We use the optional clause where to filter for results. This operation helps restrict the returned information with your requirements. This helps query your graph with your choice of specifications. There are some keywords that you may use in conjunction with the where clause. This is the Redis website for graph.query and the commands that come with it. If we look up where, which is here, these equality and inequality predicates allow for operations like looking for exact matches of node names or comparing the numerical value of certain node components. Being able to use these filters in conjunction with the where clause gives more flexibility around specifying parts of phrases or looking for names that end in a specific string. This may be useful when you are looking for a partial string match in a node. Let's return to a Redis Insight platform. How would you look for a character with particular traits? For example, I'm looking for all female characters. With initial inspection, we see that a character node has properties like name, gender, culture. So our query can specify what we're looking for in a character node. Match for a certain character where our gender is female. We return B. So that's the characters that are all female. We have 462 characters who have the gender female. How about the other predicates using inequality signs? We use them primarily for filtering for numerical values, such as the number of pages in a book. Let's match for a book node, where match b.book, where the number of pages is more than 900 pages. What does that return us? We have two books. One which is called A Storm of Swords, and another, A Dance of Dragons, both which have numbers of pages above 900 pages. Now we're getting a much better idea of what this large dataset is containing. Let's expand our matching by incorporating partial matches. In some scenarios, you're looking for string matches that are not exact matches, and this requires the flexible option that Cypher offers through predicates like contains. As an example, we're looking for all books with the partial match on their title for prints. We look for a match for a book where b.name contains prints, and we return just the name. Let's take a look at that again. Match b.book where b.name contains, that's our command. We get two results, where we got the princess and the queen and the rogue prince. The usage of predicates and the types are not limited to the ones I've shown you today, and there's a whole list on the RedisGraph query page. These optional yet very powerful predicates leverage the flexibility of the Cypher language and can fit to your needs depending on the type of questions you are asking and the insight you are extracting from your dataset. The larger the graph, the more complex and overwhelming the data will become. But once you harness the where clause to filter for results, your analysis workflow will become smoother and more efficient. Think of a scenario where you are highly curating the results of your RedisGraph query. There are multiple where statements that list out your requirements. Predicates used with the where clause may be used together using keywords like and, or, and not. Furthermore, if order is crucial to your query, there are ways to indicate precedence of certain clauses over others using parentheses. For example, I want to find the book that is published by the Tor Company or by Marvel. Let's start with match with a book where b.publisher contains Tor or b.publisher contains Marvel. And the book is less than 1,000 pages long. And number of pages is less than 1,000. Order goes left to right, and it doesn't matter here. Let's have a look at what the error is. Query cannot conclude a match, must return. Right. So return b.name. We get 3 titles returned to us: The Sworn Sword, The Mystery Knight, and The Princess and the Queen. Great. Let's bring together more concepts we're building up in this course and look at the relationships too. I want to find a house, as in a family group in these fictional books, which has female characters belonging to the house, but that female character is not associated with the northern region. How would we query this? The first part is straightforward. We match for the character which belongs to some house where. So after the where, we want to add our criterias. What is our criterias? We need the character to be female, c.gender, is female, and we further specified that the house's region cannot contain the word north. In return, the house and the character. Okay, looks like I have an error here. The curly bracket should be a normal parenthesis. We have over 270 characters and almost 200 houses that fit into this criteria. Let's do a quick look. We have House of Frey, we can do a spot check that this character, Jaina Frey, is gender female and is connected to the House Frey of the Crossing. This is a great visualization of the patterns we've uncovered in this large dataset, illustrating how combining your requirements and filters start to shape the finer aspects of the queries you make. Especially in industry, when our data changes, it's real-life data, and the questions we pose to these knowledge graphs are molded by the high-paced business needs. The flexibility in manipulating the graph can create a large impact on your industrial space. Take a moment now to reimagine your use cases for your knowledge graph. Now that you understand the flexibility and manipulations available with Cypher, you may be thinking of more advanced use cases that rely on inspecting certain domains within the data, reducing the time spent on searching or discovering new insights, or simply looking to speed up your workflow. RedisGraph has implemented index creation so that the queries optimize access to specified data. In particular, RedisGraph supports single property indexes for node labels. In this example demo graph with character nodes, the syntax might look like this. We create an index on the character, specifically the name. One of the indexes was created. You can create an index on data that are strings, numerics, and geospatial data types. In this case, we're indexing on a string. Once you've created an index, the subsequent queries will automatically refer to that index. If you've been finding that your graph query execution times have been slow, this will significantly decrease runtime and speed up your workflow. What's amazing about RedisGraph is the inbuilt capability to execute full-text searches on the knowledge graph. This is a comprehensive natural language search that takes every single word in the dataset and compares it to the given requirement. The full-text search initiation in Cypher looks like this. We start with a call command where the database has an index full-text to create a node index specifically on the house node with the property coat of arms. Okay. This will allow me to inspect the mottos used in the house nodes. To add more properties, I can use the syntax again. For instance, character and names instead of house and coat of arms. Great. Now we've successfully created this index on the coat of arms. We can match any whole words within this domain. For example, let's call for a full-text search on the keyword C. Here we switch the create command to query nodes. So call db index full-text. So here query nodes, not create node index. And we're looking for house, the keyword C. And we're going to yield the node and return node dot coat of arms. We need to yield the nodes and then to return the coat of arms containing your requirement. This is a list that we get. Here, the yield call is used as a way to select which of the available result fields are returned. This call handles the return result before it is further processed and can help filter the data for faster execution on more complicated queries. The variables set in the yield call can be renamed as new variables at this point or further modified by the rest of the query. For now, this query returns a node as it operated the full-text search. You see a nice list of coat of arms with various C-themed phrases. So how is this different from simply searching for a partial match? There is an element of natural language that is embedded in the full-text search, where the keyword can be a fuzzy match. Say I search for the word crowned. So instead of C, I'm looking for crowned. The full-text search will also match our crown and crowns. Here we have crowned. Here we also have crowned. And down here we have crown, which is a single crown. Crowned, and there's also plural crowns also here. In the backend, Redis can create indexes, a way to structure the storage of your data. Specifically in RedisGraph, the full-text search harnesses your indexing to match full words in a particular domain with the agility and flexibility required at a more sophisticated level. RedisGraph is a powerful tool that can incorporate full-text queries. How do you want to incorporate this into your projects? Take a second to reflect on all the Cypher queries in your toolbox. We have been building up the vocabulary of our Cypher queries through this class. And in this demo, I will show you how to interleave queries with the full-text search call and to interpret how good the full-text match is to your query parameters to have a deeper understanding of your operations. Say we have some vertices and edges with various information on employee names and job titles at a certain company. I've made up some names here for the company LinkedIn that employs people like Julia Lang, Julian Graph, Julia Tech, Juliano Graph, Ayaka, that's me, Julian Graph Query Demo, and they all have roles. A full-text search is a text retrieval technique that quickly finds all instances of a term or a word in a database. It's powerful because it allows for fast and accurate information extraction. Let's say that we want to find all employees with the name Julia, or partial name Julia. In order to do this, we need to create a node index to enable the full-text search on a particular property. We do this like this. We call for the database index full-text dot create node index on the person node with name. Great, now that's created. And then query for the name Julia. We know how to do this. Let's copy that over, and instead of create node index, we do query nodes. And we're looking for person, and if we're looking for a partial name, we put in these %signs around what we want to find. So we want to find good enough partial matches to Julia. Now we need to add the yield command node return node.name. So we have a few returns here. We have Julia Tech, Julia Lang, Julian, which is Julia plus an N, and we have both Julians down here. Now the fun part. Let's take this another step further and traverse the edges. Or in other words, hop out from vertices to find more information using our understanding of edges. Can we search for employees with the good enough match to Julia and find out their associated job titles? We can indeed do this by first finding the Julia vertices using full-text search, and then secondly, hop out of those vertices using the role edges. Just like the last query, we copy-paste the previous line, but just after yield, the answer, we want to change to match. We want to match the person name and dot name. So this takes the node, which now we call N. We take that N and we search for that specific person node, but we don't want to return that. We just want to match for that. And let's close the curly brackets. Then you want to traverse out into the role edge. If it has a role edge, it will traverse out of it and end up on the job title node. And now we don't want to return the original node, which is the person's name. We want the name of the job title. Great, so we don't have names anymore, we have job titles. We have HR, science lead, and 2 instructors. So we have all of the relevant job titles from these names, the 4 names that we had earlier. So how accurate was that full-text search? One metric is to look at the return score of the nodes, which is the TF-IDE score. This quantifies the frequency of the word in the node and the proximity of those terms. You can inspect the values by adding an extra variable in the yielded information and tell it to return that score. So let's go back to our more simple return of the Julia names. And here, after yield, add in score. And you also want to return the score. This will give you a score where if it's higher, it's a better match, and lower, it's a lesser of a match. As you can see from my demos, this extraction technique, enabled by the full-text search capabilities of the RedisGraph, is a big advantage of this database. This is because we can do both full-text search and graph traversal in a single database with a succinct query. Particularly, these full-text search hops on the knowledge graph are powerful as it helps denote relationships to further allow you to extract information on these relationships. Tapping into the rich dataset, RedisGraph unlocks your future to answer impactful questions within your project and more.